Okay, so today we'll be discussing about logistic regression. Okay, so it is one of the classification algorithm available. Now, if you remember from my previous videos when we talked about the predictive algorithms, let me open the mind map I have created before. So we talked about regression, right? And while talking about regression, we talked about the linear regression and different kinds of linear regression like univariate linear regression and the multivariable linear regression. We still not talk about the polynomial regression and ridge and lasso regression. These are ridge and lasso are basically related to regularization techniques. So we'll be discussing some of the topics after we discuss some of the classifications algorithm, because there are certain concepts which are applicable for both of these classifications and this regression techniques. So we will be discussing those concepts. Then only we'll be discussing the ridge and lasso regression. Then we'll move to polynomial regression. Okay. Now, if you see it over here in when we discussed about linear regression, right? Now, let me go back over here. Now, the output was basically numeric in nature, right? The output was basically numeric in nature. That means it is quantitative output. Quantitative output. Now, in classification problems, generally the output is not quantitative in nature, it is qualitative in nature. Let me give you a couple of examples. Let's say example 1, based on certain parameters, okay, I want to determine what will be the eye color for a particular person, whether it will be eye color, okay, whether it will be brown or black or blue, okay. Or my problem could be I want to determine the handwritten digits. Let's say handwritten digits. I want to classify them, right? It could be any digits from 1 to 10, right? I want to determine that by reading a particular text, okay? Or it could be a problem of fraudulent transaction. Suppose I have a transaction, right? And I want to classify the transaction whether it's a fraudulent transaction or normal transaction, right? Or it could be a problem of, let's say, by a given height and weight, I want to determine whether a particular person is male or female, right? So if you see it over here, the output in each and every case, the outputs are basically non-numeric in nature, right? So we call it as a qualitative output. So in this type of scenario, we need to use a classification algorithm compared to the predictive algorithm, okay. So this is the main difference we can draw between a predictive algorithm and a classification algorithm. Now there are a lot of classification algorithm. Logistic regression is one of them, okay. So now why the name came from the classification algorithm? Because of the nature of this output. And if you see it over here, the output we can determine as a separate class. So when you talk about eye color, my class will be brown, black or blue. When you talk about handwritten digits, my class will be 10 different classes, 1 to 10, right? And whenever a new input is coming up, I want to assign that output, right, as to one of this class, right? So suppose I was given a particular paper where by hand 2 is written, right? Reading that paper, reading those pixel, I need to convert that 2, basically predict that 2 as a digit 2. That means I will be assigning that input to the class 2, right? That is my problem statement. Similarly, for a transaction, I have to assign that particular transaction to either to the fraudulent class or normal class, right? So basically when we do the classification algorithm, when we apply any kind of classification algorithm, our output, the nature of output is assigned to a class. That's why in classification algorithms generally we determine the probability. We determine the probability for a particular input belongs to a class. Okay, probability of input belongs to a class. Okay, now if you see it over here, right, so sometimes that class could be binary in nature. Suppose like this one, the fraudulent one and the normal one, this guy over here. Sometimes it will be more than one class present, like over here or over here, right? So based on this nature we can differentiate between the logistic regression classes. Based on the classes, the logistic regression or classification algorithm can be divided as the classification problem can be subdivided into two different things. One is binary class problem, another is multi-class problem. In binary class we have only two classes. In multi-class we have more than two classes. Okay, so now based on this one, let us try to understand how we can determine the model for a particular classification problem. Now today we'll be discussing about only the logistic regression. So there are a lot of other algorithm present for classifications. So in terms of algorithm, if I just divide any classification problem, so one is this logistic regression, we have support vector meshing, we have naive Bayes, we have decision tree. Okay, so we'll be discussing one by one all of this problem. Let me see if I missed anything over here. And we have KNN, one of the important classification problem as well. We have KNN as well. Okay, we'll be discussing one by one, but in this particular video we'll be mainly discussing about the logistic regression. Now the question arrives. So suppose we will try to go by this data set today. Okay, so just go down a bit. Suppose we will just go by this problem today. We have height and weight and we have male female. Suppose we have a data set something like this. Okay, we have height, we have weight, and we have a gender. Okay, so we have height, we have weight, we have gender. Suppose I'll just take certain examples like 134, 34.5, it is female, 134, 40.1, it is male, 140, some sample data I'll be taking today. So 140, let's say 43.1 female, 140, 44.6 male. Suppose something like this. So based on height and weight, we want to determine the gender. Now the first question arrives, why can't we apply linear regression over here? Okay, so now as I said, for linear regression the output has to be the numeric in nature. So in that case we can come up with this idea of encoding, right? So if I just encode it over here, encoded version, So if I just give all male as 1, okay, and all female as 0, encoded as 0, then our this simple logistic regression problem becoming a linear regression problem, right? Because over here everything is my numeric in nature, right? You see, if I just go by this to feature, and this is my output variable, so everything is numeric in nature. So naturally we can try to see if linear regression fits into that or not, but in practical it will not, because of this one. So whenever we talk about, we said, like, for classification problem, we determine the probability of an input belongs to a particular class, right? So now when we'll apply linear regression on this particular data set, what will happen is linear regression will predict something which is greater than 1 and less than 0. Okay, now if I just draw a graph over here, we'll just try to understand through this one only. So if we just take a single feature, let's say weight, okay, and if I just take the probability here, and I'll just draw a probability line over here. So suppose if this is my probability 0 line, and if this is my probability 1 line, in this case the linear regression will, I just do separate colors. Okay, the linear regression may predict something like this. Okay, where in some places it can predict the probability less than 0, in some places it can predict the probability which is greater than 1. Okay, now as we know, our probability is always belongs to, right, probability is always belongs to this range, right, 0 and 1. So in that case, if you see, the logistic regression is actually failing over there to output that probability, or basically it is failing over there to restrict that output between 0 and 1. Okay, so in that case we need to come up with something else, so that my output is always belongs to 0 and 1. So in that case we generally use a logistic function. Now a logistic function has been defined in this way. I just give the function name as sigma t. Okay, so it is just 1 over 1 plus e to the power minus t. Okay, so now this guy is e. Okay, now Euler's number. Now if you see the nature of this particular function, okay, so if I just draw a graph for this particular function, okay, so it is always S shape. Okay, just draw it better way. Something like this, where this particular line is my probability 0. Okay, this particular line basically 0. Let's talk about probability in separate way, and this particular line is 1. So that means this particular function is capable of producing an output which is always be between 0 and 1. Okay, so now if we can use this particular function over there in my logistic regression, that means this particular function will always keep my output between 0 and 1. That means this particular function will be representing my probability, right? So that means if I just go up a bit over here, we were trying to find the probability using just normal this one, right? So when we talked about linear regression, we talked about this one, beta 0 plus beta 1 x, right? So x is a feature. Let's say we are currently working on a single feature over there, right? So if I just try to use a simple linear regression, we discussed about where it is failing over there, right? Now when we talk about the logistic regression, or basically the logistic function, here our outputs, here P is the output, as we are outputting as a probability, that's why I'm writing as a P. You can write it as a Y as well, so not a problem. So here my output will be 1 by 1 plus e to the power minus this guy, beta 0 plus beta 1 x. So this particular equation will be our starting equation for our model, right? So now for logistic regression. Now in linear regression approach, what we did, we started with this particular line, right? One of this particular line equation. Then we basically from each and every point we determine the, if I just draw the graph, whatever we did, if we just recall it over here, in linear regression approach, what we did is we started with a line. Suppose this was our data points, right? We started with a line, then from each and every data point we basically determine the difference, the error, right, from each and every point over there, right? And then we determine the total error, and then we minimize that error by rotating this line, right, either up or down, so that we are changing the slope. That means we are changing this particular, if I just go up over here, we are changing this particular slope, right? So that means we are determining the coefficient by minimizing that particular error, right? So in logistic regression also, basically we will be starting with this particular equation, and this particular equation is basically in this nature, is S shape, and we will try to fit this particular S shape graph by changing this beta 0 and beta 1. Similar approach we will be providing, we'll be following it up. Now the question arrives is how we are going to do it, because in case of linear regression it was very easy, because I was just starting with a line, and then I was just applying the least square over there, right? Now in logistic regression also, if we can find the similar kind of stuff, it would be easier for us to calculate, right? So that thing we'll be discussing now. So that's why we'll be simplifying this particular equation, and we'll try to see if we can come up with this kind of structure, okay, so that it will be easier for us to determine the coefficient, okay. Now for that, what I'll do is I will take beta 0. So now if I just take this particular equation over here, okay, and simplify it a bit, just make a line over here, okay. So if I just multiply it, it will be P probability plus P into e to the power minus beta 0 plus beta 1 x, right, equals to 1. Now if I just move this P this side of this equation, that means it will be becoming P into e to the power minus beta 0 plus beta 1 x equals to 1 minus P, right? Or if I just divide it by P by both sides of this equation, it will be e to the power minus beta 0 plus beta 1 x equals to 1 minus P over P, right? Now e to the power minus beta 0 plus beta 1 x, I can write it this guy over here, something like 1 over e to the power beta 0 plus beta 1 x, right? Just go down a bit, okay. So this we can write it as 1 minus P over P. Now if I just flip both of this, if I just divide both sides, if I just divide 1 by both of this side, it will be e to the power beta 0 plus beta 1x equals to p over 1 minus p. Correct. So now if I just take natural log, which is base of e of this both of these sides, the left hand side will become beta 0 plus beta 1x, and the right hand side will become ln p over 1 minus p. Okay, so now this particular entity over here, is called odds. Okay, and this particular entity we call it as log of odds. Now let us understand what odds means. Okay, so now because odds will play a good role when we will be determining the coefficient. Okay, so and another thing is, okay, but let us first discuss odds, then we will be discussing log of odds. Okay, so now we'll just keep this particular equation. It's a very important equation over here. Okay, now let us discuss what is odds. Suppose I have a group. Okay, in that group I have 5 male and 2 female. Okay, so now let's say 3 female. Okay, so I have total 8 members of group. Now the odds are defined in this way. If I say odds of being male, it's basically the odds of being male is, if I just count it over here, how many males are there? 5. How many in the group, how many people are not male? That is 3. That is 5 over 3. Okay, similarly odds of being female is, how many females are there in the group? 3. How many people are there in the group which are not female? Which is 5, right? There are 5 males. 5. So odds are generally defined as, for a particular phenomenon, what is the how many ways that particular phenomenon is occurring and how many ways that particular phenomenon is not occurring. That is how odd is defined. It is not similar to as probability. If I just determine the probability of being male, it will be, how many males are there? 5 divided by total number of group members, right? That is 8. So this is how probability is defined. Similarly, probability of being female will be, there are 3 females and total how many number of group members are there? 8, right? So this is how probability and odds are defined. Okay, so now if I just think about this one, if I just give this probability as name as, let's say, small p. Okay, so this particular will be 1 minus p, because there is only 2 choices we have in our group, right? So either male or female. So if the probability of being male is p, the probability of being female will be, has to be a 1 minus p, because the probability has to add up to 1, right? Now if I just see this one, if I just take p over 1 minus p, so what is there? 5 by 8 over 3 by 8. 5 by 8 over 3 by 8, which is nothing but 5/3, right? Which is nothing but odds of being a male. If I just write odds of being male, right? So this is the another way you can define odds over here. by probability. So there are two ways we can define odds, either by probability or by just simple count, right? So now that is what I have written it over here. So if I just go up now, this particular thing, right, p over 1 minus p, it's basically odds of being a particular input to belongs to a particular group or class, right? So now why, then the question comes up, then why log of odds we need to take? Okay, so to do that, if I just analyze this particular equation over here and draw a graph of probability versus odds. Okay, so here in my x-axis it will be probability, here it will be odds. So you can see it over here, when my probability is 1, right, over here, so that means my odd will becoming 1 by 0, right? So that means it is infinite. That means when I'm talking about probability, and this is probability of 0, and if this is 1, the odds are becoming infinite, and my probability is 0, it is 0 by 1 minus 0, that means 0. So if I just draw a line over here, graph over here, the odd versus probability will look something like this. That means when the probability is increasing, odd will increase a lot till infinite. Okay, so that means odd will always vary between 0 and positive infinite. Okay, so now this causes a problem. Maybe I will just give you this kind of intuition. It would be better, right, if I just say odds of being male is 5/3, right? Now odds of being female has to be just opposite of odds of being male, right? So if I just calculate this one, 5/3 over here, if I just open Google, okay, and just give, so give log, sorry, 5/3, 5 over 3, right? So what is the answer? It is 1.66, right? So if I just write it over here, so it is 1.66, and 3 over 5 is 0.6, right? So ideally it would be nice if my odds of being female will be exactly opposite of this one. So this is not the case of odds, but if I just take log of odds, let's see what is happening. See, if I just take log of 5 over 3, so if I just go to Google over here, okay, and if I just give log of 5 over 3, so it is 0.221. Let's take it down. So natural log of 5 over 3 is 0.221, and if I just take natural log of, so we'll just take 5 over 3 first. I think before I take normal log, it is 0.510, so it will be 0.510. And if I just take natural log of 3 over 5, let's see. So if I just take natural log of 3 over 5, it will be minus 0.510. Minus 0.510. If you see, this is better representation compared to the normal odds, right? So that's why we generally take log of odds, so that if I just draw a axis over here. So if my odds are, if I just change the color, if my just odds are varying from 0 to positive infinity, it can be shown that logs of odds are actually varying from negative infinite to positive infinite, okay, with 0 over here as a mean. So how to do that? If I just analyze this ln of p over 1 minus p, okay. So when my probability is 0, let's say, so this equation is becoming, so if I just do the math over here, so ln of 0 over 1 minus 0, that means ln of 0, so this is negative infinite. And when my probability is 1, it is ln over 1 minus 1 minus 1, that means ln 1 by 0. Now log 1 over something, x over y, is log x minus log y, that means log of 1 minus log of 0. Now log 1, we know it is always 0, minus log of 0, it's defined as negative infinite, that means it will be becoming positive infinite. So if I see it over here, that those two boundary values are actually telling me that my log of odds will vary from negative infinite to positive infinite, right? And now if I just go over here to our data set and plot these guys over here, okay. Now in my current data set we have that male female, right, and we have decoded them as a 0 and 1, right? So all the 1 guys will be belonging somewhere over here to the positive, because when the probability is 1, it will be somewhere over here clustered, and all the zeros, if we just change the color, all the zeros will be belongs to somewhere over here clustering, okay. So that means now I can draw a simple line over here, okay, just to draw a boundary between these guys and these guys. So that means I actually got an idea about from this how to convert or how to transform this particular S-shaped graph to a linear graph, because if I just see this particular log of odds equation, the left hand side is a linear one, right, because it's a linear combination of features, correct? So that means it has to be a linear graph, right? So, and that graph will basically help us to determine the coefficients, okay. So we'll see in the next video how to determine that one. We cannot apply normal least square over here. There is some reason behind this, because this is belongs to positive infinity and negative infinity. That means our square terms, that means our error will becoming infinite. So we have to have some other ways, and the way name is maximum likelihood. We'll discuss that in next video. But at least we have some mechanism to convert this particular S-shaped graph to this one, so that at least we can apply some of the other mechanisms to find the coefficient over here, okay. So if you see it over here inside the logistic regression, somehow the main linear regression hidden somewhere over here. We have discussed that one as well. And another way to see or depict this particular log odds equation would be like in this normal logistic regression equation, whatever we have discussed over here, there is actually no way to know if I change beta 1, so that means the coefficient of a particular feature, right? So how the probability will be changing, there is no direct relationship over here, okay. But over here we know if I just change beta 1, okay, the log odds will be changing over there. So we have at least have some kind of direct correlation between the feature coefficients and the probability over here through the log odds, okay. So this is another way to see that one. So hopefully I did not confuse you guys. So the main thing we have done it over here is we defined the logistic regression. We started with our main logistic regression or the logistic equation over there. Then what we did, we basically need to set or we need to fit this particular S-shaped graph to our data, right? And we basically try to do similar kind of way whatever we have done using the linear regression, using using the least square over here, right? But to do that, we need to convert this S-shaped graph to a simple line, normal line, linear line, right? So that is what we have done it through log odds over here. Okay, so now another problem comes up. Because of this infinite, we cannot apply least square, so we'll be applying some other formulas over here. Hopefully this this intuition at least useful for you guys. And similarly, for I have shown you just for single feature. Now for multiple features, we just have to add those features over here. So for multiple features, our probability equation will be coming something like this. It will be 1 over 1 plus e to the power minus e to the beta 0 plus beta 1 x1 plus beta 2 x2 dot dot dot, right? So this will be just like we did for linear regression, the base setup we have done. For logistic regression also similar way we'll be studying our setup. Okay, so if you see, the logistic regression is mostly useful for binary kind of classification, where we are just classifying whether a particular input belongs to set 1 or set 2. Okay, so in next video we'll be talking about maximum likelihood to determine the coefficient of beta 1, beta 0, beta 2. Okay, see you in next video.